Alright, let's get started. In this video, we will be doing a sample problem for the design of belt conveyor. The problem says design a belt conveyor having the following requirements and information. The material is bagasse and the required capacity is 50 tons per hour. And note that this tons is the English tons, which is equal to 2,000 pounds. And also the problem says we are to use 20-degree trough angle, and also assume lump size is equal to 2 inches, so meaning that the size of the bagasse is 2 inches, and all lumps and no fines. Using a pulley having this relationship of 4D, that's 4 times diameter, is equal to the belt width, or we can just write D is equal to B over 4, and also assume that the drive efficiency is 0.85. In the figure, it specifies the dimension, the horizontal dimension and then the vertical dimension from pulley to pulley. So we have 200 feet along the horizontal and a 50 feet along the vertical. Okay, so this is a design problem. So again, when we say design problem, we are given the loads or the required capacity, and then we are to specify the dimensions of the belt conveyor. Okay, I'd like to point out here that in practice, the usual information that's probably given would be this one, the material and then the capacity. Now this one, I just included it here so that we can be able to solve directly our problem. Okay, and the choice of this, why use the 20-degree trough angle, is because of its flowability, the material. But if it's not given, then you can actually find it out. You might want to select the flat belt or a trough angle with minimum degrees. And the lump size, this is just my assumption for now in this homework, that's 2 inches. And all lumps no fines. And this one, you use swing pulley for D is equal to B, because there must be some relationship where I can compute my pulley diameter. So I just made this relationship. But if there are standards or methods in obtaining the diameter without, different from this one, then that's also fine, I guess. Anyway, what's important would be the belt speed, and so if I can make this assumption with the diameter, then I can find out my RPM, right? If you recall this relationship, V is equal to pi dn, so relating the linear speed of the belt to the rotational speed of the pulley. Okay, and then this n will be the basis for the selection of the speed of the electric motor. Okay, and this one is also assumed is equal to 0.85. Okay, so let's get started. Okay, so in any problem, the first step is to obtain the necessary information. Okay, so in obtaining the information, we are to consult table 3-1 and 3-2 of SEMA 5th edition. Okay, so what we get is we have a material, bagasse, and its material code is E45Y. and that means this is our size, this E, and then this one is the flowability, and this one is the abrasiveness. So flowability is 4, and what else? In the table you can also obtain the density. Density equals 8.5 pounds per feet cube, and our angle of repose is equal to 45 degrees. Okay, so if we check the table 3-1, so you see here the flowability of the material, and we have number 4. So if we have number 4, then our angle of repose would be in this range for 40 degrees and up, and therefore our surcharge angle is 30 degrees. So therefore surcharge angle is 30 degrees. Okay, so far that's what we need. So the next step is to select belt speed. Okay, so in doing so, we need to consult table 3-2. Okay, so here's our table. Sorry, that should be table 4-1. So this is not 3-2. This should be a 4-1. Okay, so for table 4-1, we have this recommended maximum belt speed. So here in the first column, it says material being conveyed. So we have to check what is our material. And if we check this one, green or other free flowing, that's not it. Coal, the second row is not. Also, third row also not. This one, which is not. And this will be our selection because it says non-abrasive materials discharged from belt by means of plows. Okay, so we have a non-abrasive. This is also non-abrasive, except that it says grain or other free flowing. So this will be it. And it says here our belt speed is 200, except for wood pulp, and where 300 to 400 is preferable. By the way, this sugar bagasse is actually ligno. The term there is lignocellulosic. So something like, it's more like wood as well. So it has a heating value, maybe not close to wood, but quite high as well. Okay, so anyways, for us here, we'll just say we'll just use 200 feet per minute. Okay, so we have an irregular material which is sluggish and non-abrasive. By the way, how did we know that we have a material that's non-abrasive? Because of our material code. So we have 5, which means non-abrasive. Abrasive, and this one is sluggish. So therefore, select 200 fpm, and in the table it says that applies. That's the maximum recommended maximum belt speed at any belt widths. So if we have selection for for example, something like this for the grains, then you can see that regarding this I mean with this belt speed, then you have this belt width. So I guess we will do iterations after we get into the capacity table, because it has to be within this belt width specifications. Okay, so now let's move on. The next step is to solve for equivalent capacity. Okay, so CE is equal to CV required times our this is an equation 100 FPM all over selected belt speed. Okay, so CV required, which is just mass divided by the density, and we have we have 50,000. Okay, so that's tons per hour, and we have 2,000 pounds per ton, and times our density, the reciprocal of density, which is 8.5 pounds. Okay, times 100 FPM, and this one is also in feet per minute, which is 200. By the way, this is not 50,000. This is just 50, because 50 tons per hour. So 50 times 2,000 divided by 8.5 times 100 divided by 200, we have 5,883 feet cubed per hour. Okay, so that is our equivalent capacity. Okay, so after that, we can now determine belt width, and in doing so, we need to enter table 4-2. Okay, so this is now our table, and we have here the 20-degree trough belt. Okay, so if in our homework we have a different trough angle, then you have to go to the corresponding table. So maybe 4-3 or 4-5 or whatever. Okay, so that's 20-degree trough belt, so that's fine. And then our surcharge angle. Okay, so this will be the row, and we have a value of 5,883. Okay, so if we select here, so we have 5765, and then the next one would be 7997. Okay, so if you notice, if I mean the 5,883 is more close to this value 5765, but in our computation, I mean, just for the sake of a classroom discussion, then we'll just have to select this higher value, because I guess, I mean, in my opinion, we are just solving for a range. So this one, if we select this one, then probably we can adjust some speed or some details, or some parameters, and we can get a narrow belt width as compared to this 42. Okay, so meaning that if we have this lesser material, then probably we can reduce some cost. Okay, anyways, it's just one of the many factors in design. Okay, so back again to this homework. In this class, we'll just use the next higher value. Okay, so 7997, and that's gonna be 42 inches. So belt width is 42. Okay, 42 inches. Okay, so you have to check again. Check belt width at maximum belt speed. So that's gonna be, if we go back to table, I guess table 4-1. So table 4-1, it says 200 fpm at any belt width. So meaning, therefore, no problem. Just write no problem. Okay, so next step is to check the lump size, maximum lump size. We check max lump size. Okay, so we have a 30-degree surcharge angle. Therefore, our equation for checking it would be b all over 10. Okay, that's in our handouts, but also it's expressed in terms of statements in the handbook. Okay, so max lump size, just write max lump size is equal to, our belt width is 42, so 42 all over 10, and that's going to be 4.2 inches. So we see that 4.2 inches is greater than our selected, our material lump size, which is 2 inches. So therefore, no problem. Okay, so if it happens that we have a maximum lump size allowable less than the actual lump size, then we have to select another belt width. Okay, so now the next step is to solve for the pulley face width and diameter. Okay, so step number 6, solving for pulley diameter and pulley face width. Okay, we have this relationship 40 is equal to b, and therefore our diameter is equal to b over 4, which is just 42 all over 4, and that gives 10.5 inches. Okay, so recall that in pulley, standard pulley size, we have I think that's just 8, 10, and 12 in an increment of 2 inches. Okay, so we have 10.5, so therefore we'll have to round it off to 10 inches. Okay, so therefore use dp is equal to 10 inches. Okay, so now we have this pulley diameter. Then the next step is to solve for the width of the pulley. So the width of the pulley is, first we have to determine the belt width, because that depends upon the allowance, or the spacing. So b is equal to 42 inches. So therefore our face width would be b plus 2 inches, because as long as you have a belt width up to 42 inches, then you just have to add 2 inches for the spacing. but if you have a belt width greater than this, then we have to add 3 inches. So therefore our pulley face width would be 44 inches. Okay, so now sketching, let's sketch for now, although it's not yet done. Sketching our preliminary design. Okay, so we have this pulley and we have this belt. Okay, and okay, we have this belt. This belt width of 42 inches. Then this one is 44. Then this one, the diameter is 10 inches. We have a belt speed of 200 fpm. Okay, so far so good. Then the next step would be to calculate the I guess we should include this one. Calculate the pulley speed. Okay, so since we have the belt speed, so pi d, that's the diameter of the pulley, pi d n, and n therefore would be equal to the belt speed divided by pi times the pulley diameter. But this belt speed is in this is in feet per minute, right? And this one is in inches, so we have to convert this 10 inches times 1 over 12 inches, that's 1 foot. That's gonna be 200 divided by pi times 10 divided by 12, and we have 76.4 rpm. Okay, so we need this data so that we can size up our electric motor. I mean the electric motor as well as the pulley combinations, the drive transmissions, and things like that. Okay, so the next step is to solve for, from this step onwards, we are going to calculate the horsepower requirements. But recall that the total horsepower is equal to the friction horsepower plus the horsepower required to lift the material plus the horsepower required to convey the material along the horizontal. Okay, HP sub h. So let's say solving for the friction horsepower. Okay, so in doing so, we are going to enter figure, I think that's figure 6.17. And in doing so, we need the following information. B, our belt width is 42 inches, and our material density is 8.5 pounds per feet cube. Okay, so this is it. This is our table, and we first have to go into this table first, and we have the belt width in the first column, and we have this material, I think that's the density, the density. So what you see is we have a belt width, and we have this material, let's just say density. And then we have, since we have 42 inches, okay, so 42 inches, but here the selection is 50, then 100, next is 150, and then 200. Okay, so our material density is 8.5, which is less than this. So meaning we have to do interpolation or extrapolation. Okay, so what would be the value here? Okay, so we have this in the 50, we have a value of 36. That's 36. And this one, for the 100, we have 40. Okay, another way to do this actually is, since when we're doing the I mean interpolation, we're referring to linear interpolation. So I guess we can just also use the similar triangle, I guess. So it's like this. Let's say in our x-axis we have the 3 points. We have 8.5, 50, and 100. Okay, so 8.5, 50, and 100. And of course, what would be the value here? Okay, so for 100, our value is, it says 42. Then this one is 36. Then this one is our unknown. This is actually what we are solving. Okay, so by similar triangle, you can actually solve for the value of x. 42 minus 34 all over 100 minus 50 is equal to 42 minus x, 100 minus 8.5. Okay, so take note that this is just my assumption. I mean, and also this is the most easy interpolation, rather than go for quadratic interpolations or higher degree. This is much easier and practical, I guess. Okay. By the way, there's a note in, I think in the handbook about the actual values for this. So rather than going on, rather than going on in this table, and it relates to some other chapters. Anyways, for us here, we'll just stick with this, and you have this equation now. So you can solve for x, and if you do the math, you get 27.36, or let's just say x is equal to 28. Okay, so that's the value of, that's the weight. Okay, this one, the values here, it's the weight of the mechanical components without the material. Okay, so it's just an estimate. That's gonna be pounds per linear foot, of belt width. I mean, of belt width, not the belt width of. I mean, I don't know if it's belt width or belt length, but it just says linear foot, so let's just leave it like that for now. Okay, so once you have this, then you can go into the table. Okay, so it says 28, so this one is, okay, so we have 10, 20, and 30. So our line would be somewhere here, right? And our horizontal center is 200. So meaning we are here, so we are to project up to the 28 value line, diagonal line, or let's just say 30, and then project it to the left, to the vertical axis. And that's just okay. So that's the problem with this, I guess. If you have a shorter length, then it would be hard for you to determine the value. Okay, so let's just say we have a 0.5, okay, 0.5 HP. Okay, by the way, I think I don't have much time for now, so we'll continue our computation in the next video.